So, so your JEE exam is when? When are you giving your JEE exam?
January 26th to February 1, sir.
Okay, that's the first attempt, right? Okay, so what's your strategy like? Not just one chapter, no, SHM. We have to plan for the full thing.
And sir, right now I'm okay with SHM because we had an exam like day before yesterday,
Okay.
and then there I scored really good marks in SHM, so I don't think I would need more help in SHM. So
yeah, that's what I'm saying. So we have to plan to target the JEE exam, right? So once after discussing with your mom, I will. I'll give you a plan so that the full thing is covered, right, before the exam. So how much did you score in today's test?
I scored 72 in physics.
Out of?
100.
Okay. So previously you used to get how much?
Previously, I won't even used to get 40 also. So like I used to get 40 or below 40.
Okay, fine. Okay, I think we should not just jump to conclusions. We just have to wait for some more time. Okay, so what do you want to discuss today?
Sir, I have a like this thing because I have work energy, power and rotation dynamics, which I didn't cover at all. Like I don't know anything from that. Like anything in the sense the basic
power. Sorry, work energy and power, right?
Work energy, power and rotation dynamics both.
Yeah, work energy power is a relatively easy chapter. Rotation motion is supposed to be the you can say toughest and interesting chapter of class 11. So right now, what do you want to do? We'll start with the easy one.
Okay.
So work energy and power. Chapter 6. So you're following NCERT text or some other text?
What's it?
For your studies, for school board exams, it's a CBSE, right? Yeah, so you're following this one. NCERT only, right?
Yeah.
So, you did long time back.
Very long time.
This one, and are they teaching this again in the coaching? Or so do they teach 11th
No.
or give the test for 11?
So they taught 11th when I studied 11th. Like that time they taught all of that. They didn't teach it later on.
Okay, so what is the definition of work done? How do you find work done?
Force into displacement.
Yeah. So if it is like a small displacement, the corresponding work done will be
F into S.
It's actually, if you want to be more strict, it's vector, right? F dot B.
Okay.
So it's dot product of vector, and this is since a work done over small displacement, we call it DW because D stands for small. So this displacement is small. So the corresponding work done is small work done, which we call it DW. So the basic thing is vector. If I have two vectors A and B, I can multiply them, right? So one way to multiply is the dot product. So this is equal to what is it? A dot B.
AB cos theta.
Where theta is the angle between A and B. Okay, so this I can interpret as A into B cos theta. So B cos theta is projection of B onto A. Or I can interpret this as A cos theta into B. This is projection of A onto B. Like you have two vectors, A and B. Theta is the angle between them. So A dot B can interpret like this. This distance is how much? Sorry.
This distance is A dot B by mod A.
No, this distance. How much is it? It's B cos theta. This is a right angle triangle, right?
Yeah, sorry.
Correct. Hypotenuse is B, so adjacent side is B cos theta. So A dot B can be interpreted as A into this projection of B onto A. I can also write this as I can project this as I can extend this line and drop a perpendicular from here. Okay, 90 degrees. So this length is how much?
B sin theta.
No. I didn't draw it properly.
No, wait.
So this is A, right? The length from here to here. That is A cos theta. Because the same right angle triangle. Okay, hypotenuse now A. Okay, so the adjacent side is A cos theta. So this is same as B into A cos theta. So we can interpret this in either A into B into cos of angle between them, or it's A into the projection of B onto A, or B into projection of A onto B. A cos theta is projection of A onto B. Okay, so if this force is uniform over this whole displacement, then W is obviously integral dW. Will become integral F dot ds. In a simple case, okay, even if say F ds cos theta integral over the entire path. Okay, so this force is uniform. That's not changing from face to face along the path. And I say theta in a particular case, it's say simple. Say theta equal to 0 degrees. Simple case. So it become F into integral ds, which is equal to F into s. So work done is F into s if the force is uniform and the angle between the force and the displacement is 0 degrees. So this is valid in general, I mean always. This is valid only for force which is uniform and the displacement is in the same direction of the force, that is theta is 0. Okay. So in the case of non-uniform force, the total work done means I have to do the integration. So this is an example of a force as a function of space. We have taken only 1D, so only x has been taken, no y and z. It will become complicated, right? So just the x variation of the force is like this. So it's not a uniform force, it's a force which is varying as a function of x. So here the work done to move from xi to xl. I is initial, f is final. There'll be integral of f dx, because f dx is work done over a small displacement dx. To get the total work done from xi to xl, we have to integrate this dw over the limits xi to xl. And interpretation of integral is area under the curve. What is interpretation of derivative? Geometrical interpretation of derivative.
Integration of derivative.
No, geometrical.
The function which is there, that will only come.
Say I have a function y versus x, where y is f of x. So this is x, this is y. Okay, there is some function y equal to f of x. So at this point, if I find the derivative, that's dy by dx. What is the meaning of it, or interpretation of it? Geometrical interpretation. At this point, if you draw the
slope,
tangent, the slope of this thing is dy by dx. So this is geometrical interpretation of the derivative. Similarly, I can have an interpretation for integral y dx from
area under curve.
Area under the curve. So from xi to xf. So integral of this function from between these two is the area under this curve. So here, this work done is the area under this curve. Okay. So delta x means small interval. Dx means very small, infinity 7. So delta x tending to 0 is dx in some sense. That you know, right? Delta x is a finite length. Dx is very small length. It's almost tending to 0. That is the difference between delta x and dx. So
f of x is a force, sir, variable force.
Sorry? Force is variable.
F of x is variable force, sir.
Yeah. F of x is variable.
Okay.
What I'm saying is this force I can write as summation of this one, right? Okay. When delta x becomes very small, dx. Difference between delta x and dx is delta x is small interval in x.
Okay.
Dx is very small. In the limit it tends to 0.
Okay, sir.
Then in that case, summation will become integration. Like, see here, they have written, right? Delta x tending to 0, summation, when tending to 0 will become integral. So in some sense, the integral is infinite summation. When delta x becomes very small, number of intervals become infinite, right? Go from xi to xi. Delta x have some small value, then there will be finite intervals. But if delta x is very, very small, tending to 0, then this summation will become infinite. Then that summation of this area or the area will become exactly the area under the curve. This summation will become this area where this small error is there. Okay, so that error will go when I do the integration. Okay, so work done by the variable force is this one. We have to integrate. When I do the integration, I'll get this area. When I do this infinite summation, I'll get this area. So there is an error right here. This one, this small area is left out. When I do the integration, I'll get this proper work done. Okay. So just try this example. You might have tried this earlier. A woman pushes a trunk on a railway platform, rough surface. Just read the question fully. Understood the question?
Yes, sir. Yes, sir. One.
So okay, so she applies a force of 100 Newton for a distance of 10 meters. That's the initial 10 meters. After that, she gets tired. So the applied force is reducing linearly to 15 Newton. Okay, and the total distance covered is 20 meters. So the first 10 meters is a constant force of 100 Newton. And from 10 to 20 meters, the force is decreasing from 100 Newton to 50 Newton. So it's a variable force. If you consider just 0 to 10 meters, it's a uniform force. But from 10 to 20 meters, it's a variable force. The force varies from 100 to 10. Okay. So plot the force applied by the woman and the frictional force, which is 15 Newton versus displacement. Okay, calculate with the work done by the two forces over 20 meters. Straightforward question. Only the first step you have to draw it properly. So just try to draw the graph. Applied force versus the x.
They have said it's linearly decreasing.
Linear means straight line. See, I can decrease from one value to another value by different ways. No?
So
this is x.
we can.
So this is the initial force, 100 Newton, and this is 50 Newton. So from here to here, I can decrease like this, But he's saying linear, so it's decreasing straight, as a straight line.
So we can do integral directly.
Yeah. So the force versus x diagram will look like this. For the first 10 meters, it will be this straight line of value 100 Newton. And from 10 meters to 20 meters, the force will decrease from 100 to 50. So this is the force as a function of x. And this is my x. So find the work done now. Can you do it?
Sir, 1 minute.
Yeah.
We are seeing that force is reducing linearly with distance. So I can write f as some minus kx, something.
Yeah, that
a constant.
So if work done is integral f dx, no?
Correct.
From 0 to 20 meters. Right?
Correct. 0 to.
Yeah, 0 to 10 is constant force.
Oh, so 0 to 10 we are splitting integral. 0 to 10 will be 50, and then 10 to 20 it will be 100.
No, for 10 meters it's a constant. Up to 0 to 10 is a constant force. After that, the force is decreasing. Okay, the basic thing is it's area under the curve, right? area under fx curve. So you just have to find this area. That will give me the work done.
Okay, I'll do.
Get the answer.
0 to 10, it will be 50 into dx.
Not 50.
Plus
100, no. Area up to
oh, reduces 100. And then 10 to 20, it will become 50.
Yeah, that will become a rectangle plus triangle.
Okay. 50x from 0 to 10 plus, sorry, 100x
0 to 10
from
meters, I have to find area of this rectangle. This is the work done from
Okay.
0 to 10 meters. For the next one, it will become a trapezium, or I can make it this as a rectangle plus triangle. That will be try to find area of this rectangle, and then area of this triangle. That will be the total work done.
Okay. 1000 plus 1000 minus 500. So it will become 1500 joules.
Work done from 0 to 10 meters will be 100
1000
into 10 plus this part will be 50 into 10, and the triangle will be half into base is 10 into height is 50.
No, don't like it.
This rectangle, this length is 50, right?
Okay.
Sorry, the length is 10, but this vertical height is 50. Horizontal distance is 10, but this vertical height is 50. So it's 15 to 10, and the triangle is half, base is 10, and the height is 50. Because this one. So what is the answer?
No, I'm not getting 1500.
1000 plus 500, 1500, and then this is plus 250, 1750. That many joules.
Then, sir, but if you integrate, then I'm getting different answers.
Integral is you don't have to do the integration because see you have to get the function, no, first of all, to do the integration. So the first part, the integration is from 0 to 10 meters. Okay, so it's a constant function. So if you do the integration, I'll do it.
Okay. So when we don't know what the function is, we have to do like this.
You actually know the function, but finding the area is trivial. So this integration is from 0 to 10.
Okay.
Plus the integral of, I have to get this equation of this line. Okay, that will be difficult. No, not difficult since it's I have to get the equation of the line. So y equal to mx plus c.
Okay, sir, understood.
So to get the equation and then do the dx from 10 to 20. That's not required because you have this interpretation.
Since we don't know.
Area under the curve. No, it's not don't know. I can get the equation line, but it's a lengthy process. To get the equation line, I have to put y, which is say 100 minus y divided by x is 10, right? 10 minus x, it's equal to slope, which is 50 by 10. So this is the equation of the line. So from this, I'll get 10, right? So I'll get 100 minus y equal to 5 into 10 minus x. So this will become y equal to 100 minus 50, so it will become 50 plus 5x. So you can check whether this equation is correct or not. If you put x equal to 10, I have to get y as 100, I'm getting. And if I put x equal to 20, some mistake I made, y 100 minus y divided by 100 is this one, and 10 equal to minus, right? Negative slope. Minus sign. This 50 is going down, right? This minus this or divided by x1 minus x2 will be 10 minus this one. So slope is negative for this because it's going down, right? This line. So minus sign has to be here. Okay. So it will become plus 5x, or either I should say minus 5x. Y I take it on the right side. Minus 50, so it becomes 150. Okay, so if you put x equal to 10, it will become 150 minus 100 is 50. Again, mistake is there. Minus 1 divided by 50 over 10, so it's correct. So minus 5 into 10 minus 6. 100 minus 1, so y equal to plus 5, so we get minus 5x. So when I put x equal to 10, that's correct. I'm getting 100. And when I put x equal to 20, it's correct. When I put x equal to 20, this is 100, right? So it'll become 50. So this equation is correct. So this thing, the here will become 150 minus 5x. Now we can do the integration. Okay, but this is a lengthy process. You don't have to do.
Sir, but if we don't know the function, we can directly do this, like get it from the graph.
Yeah. This is a simpler one. That's what they have done, no? Area of rectangle plus area of trapezium. This trapezium, which is nothing but rectangle plus triangle. Or you can remove the formula for trapezium. It's average of this two sides and then the distance between the two parallel sides. It's average of these two sides, which is 100 and then 50, and then the distance between the two parallel sides, that is 10. Trapezium will have two parallel sides and the other two sides. So the two parallel sides will have unequal length. So you take the average of them into the distance between them. So average of two unparalleled sides, or sorry, parallel sides, and the distance between them, 10. So that will give you the area of the trapezium. Okay, so this is work done by the applied force, but the friction force will be a constant force like this, and they have put minus 50 because it's opposite to the direction of the displacement.
Why minus 50? Again, we have to take us.
Hold on. This is the platform, right? This is the luggage or something. So suppose the luggage is moving this way. I'm applying a force this way. This is applied force. So displacement is towards right, and displacement also to. So this applied force also towards right. So F dot Tx will be positive because it's F into Ts into cos 0, because both are in the same direction, right? And cos 0 is plus 1. Okay, but the friction force will be opposing the motion, right? So this is the direction of the friction force. Okay, so friction force dot
that will be equal to F dot ds.
So it becomes F into Tx into cos 180 degrees. So this is minus 1. So I can consider the force as a negative force. Basically, F and Dx are in opposite direction, so the work done will be negative. Okay, so I can get a negative area if the thing is downwards, because area above the x-axis is positive area below the x-axis is negative area. Like you have slope, you have positive slope and negative slope, right? This is positive slope. Suppose the curve is going down like this. At this point, if you draw the tangent, this is a negative slope because it's going down. This is a positive slope. Similarly, I can have positive area and negative area. This is a positive area. And suppose the curve is going down like this. And I want to find area between these 2 points. So this area is negative. Okay. Like positive to negative, I can have positive area and negative area. The area here is also negative, but the area is, if it is above means it's positive. So it does not depend on the value of x, it depends on the value of y, whether it's positive or negative. Or you can think the area is y into dx, small area. Dx is always positive because I'm increasing x. So the sign of the area depends on the sign of y. So y above the x-axis is positive area. Y below the x-axis negative, y is negative, so negative area. So the work done is.
But when taking, we'll take.
So force, I can assume the direction towards right as positive. So force is a vector, no? and it's a 1D vector. So 1D vector, I can give the direction by taking the sign. One direction I will assume is positive, which is the right direction. So according to that convention, this friction force is the opposite direction, so the value should be negative. Negative indicates the fact it's opposite to the positive direction, which I have taken as towards right. Okay, so this area is area of the rectangle with a negative sign. It's a negative area. And this area force is constant throughout. It's not a variable force. That's what they are shown here, right? It's a constant force. Sorry, uniform force. Here the force is variable. From here to it's uniform. After this dropping down. This is a constant force, friction force. Friction force mu to n, or in this particular case, mu k into n, because mu k is kinetic friction, right? Once it's moving, it's a constant friction.
Because it's moving, so.
It's a constant friction. Static friction, the maximum value is mu s into n, but before it moves, it can be less than that. Maximum friction force is mu s into n. But once it starts moving, it's always the same constant friction force, which is mu k into n. And they're given the friction force value straight away, 50 Newton. Okay, so negative area of the force. Okay, negative area of the force. So in some sense, the work done is negative in the sense that actually, by the upright force does work on this box or the luggage or the trunk to move it towards right. But this friction force is not actually doing work, no. It's actually consuming some energy.
Okay.
Okay, this is the most important concept of this chapter, which is work energy theorem. Okay, so remember or not, you know, conservation of energy, right? Energy is conserved. But the thing is, okay, energy conserved is initial energy equal to the final energy. Right now, suppose let me take this example for box on a rough surface. So it's moving, say initial velocity u equal to 5 meter per second. So it'll move towards right, and because I'm initially it's moving towards right. Okay, so after some time, what will be the final velocity? Friction is there. Friction force.
It will reduce. So
because of friction force, there is no upright force, just the initial velocity, and then you're just leaving it free. So because of friction force, the velocity will keep on decreasing and become 0. Okay, so in this case, the initial energy is half m. Okay, the meeting will get cut. You have to rejoin again. Okay, after 10 minutes, not now.
Okay, sir.
Okay, so initial energy is half m u square, which has some value, or half m pi square. Final is half m 0 square. So this is not.
So 0.
So it's not valid, no. So energy is not conserved. But what you have to do is you have to include the work done by the system. Final energy is less, no. So work done by the system will add to the final energy. Work done by the system will add to the final energy. Because if the work is done by the system, it will lose energy. So final energy will be less than the initial energy. So you have to add the work done by the system to the final energy. And work done by the systems is to overcome this friction force.
Work done by the system.
So the friction force is mu into n. So the work done by the by this thing is to overcome this friction force. So it's mu into n into the distance traveled before it stops. Okay, so if I add this thing here, then this equation will be valid. So work energy theorem is adding this. So to the initial energy and the final energy, we have to equate this. We have to add work done by the system to the right side. Only then this will be equal. Rather than this work done on the system will increase the final, will increase energy. So in that case, final energy more than the initial energy. So work done on the system, I have to add to the left. Understood? No? Just assuming the first case, only work is done by the system. So this term is not there. So in that case, the work, if the work is done by the system, final energy will be less. So to the final energy, if I add the work done by the system, I'll get the initial energy. When work is done on the system, the final energy will be more. So that work done on the system, I have to add to the left side. So this whole thing is a work energy theorem. So this is what they have written here. added some different form. They just consider the kinetic energy. So here, work done on the system will increase the energy. So initial kinetic energy plus the work done is the final kinetic energy. Okay, this they are just taken only the kinetic energy. Here I give a general statement.
Sure, but then the work on the system will go to the other side, no, because it is negative, right?
No, I'll just show. So this is the same block with the initial velocity be 0. Okay, then I'm applying a force F. Because of that, it acquires some velocity V. Let's say 7 meter per second. Okay, so here now the force is doing work on this block. Initial energy is half m 0 square plus work done by the force will be half m 7 square. So whenever work is done on the system, its energy will go up. Whenever system does work, it will lose energy.
The system does work, it will be positive, like it will be more.
Yeah. Because the force and the displacement are the same direction. No.
Okay.
Sign you can fix by physical reasoning.
Sir?
The sign of the work done, you can fix by physical reasoning. Okay, because if work is done on the system, that positive quantity, if you add to the initial energy, they'll give you the final energy. So since the final energy should be greater than this initial energy, this has to be positive.
Okay.
Similarly, when the system is doing work, it's losing energy, right? So initial energy is more. In that case, this work done by the system has to be positive. Okay, here the initial velocity is there. So work is done by this block to overcome this friction. In the process, it loses energy and becomes 0. Velocity becomes 0. So work done by the system here is positive to add to the final energy, which is less, to give me this more initial energy.
Okay, understood.
So this one. So this you can solve by work energy theorem. Let's read this example.
Retarding force given. Notice the final kinetic energy and speed Vf of the block. We know EF minus EI is equal to work done. Work done defined. F dot dx. So, EF I'm supposed to find means EI half into 4 equals to integral of minus k by dx from 0.1 to 2.01.
First step to solve the problem is to draw a sketch, okay, and transfer all the information in the question to this whatever diagram you have. So block of mass 1 kg, so that you have to read the question only once. Time is not wasted again. And horizontal the speed, so VI is 2 meter per second, and it is a rough patch from 0.1 meter to 2.01. Since it's a rough patch, I know something like this. Figure should be as clear as possible. From here, it is smooth, so I'll make it rough here, just for understanding. Okay. So here obviously there is a friction force, no? That is Fr. We'll try to slow it down. So direction of the force will be opposing this motion, will be towards left. Okay. And this Fr is given as minus K by X. Okay. The K is some constant which is 0.5 joules. Okay. What do we find the kinetic energy? So we have to find the energy kinetic at this point, Kf, and also Vf.
Mm.
Once I know Vf, I know Kf because mass is given. So I have to find the velocity at this point. So how do you do this one?
Delta Ke will be equal to W.
Work energy theorem.
Mm.
Right. So you can get the energy at this point. Then we call this point as I. So what is energy at I?
Energy at I will be equal to half mv square.
Because there is no dissipation from here to here, it's smooth. So velocity will not change. So half m 2 square. Right.
They've given ms1. So.
Then we'll put it later. And at this point, EF will be half m.
Here we are supposed to find.
Yeah, Vf square. Okay. So are these two things equal? Yes or no?
No.
No. I just had to add the work done by the system to this.
To add a work done.
Finally, will be less because there's some dissipation. So work done by the system or by this mass. If I add to this one, I'll get this one. So now I can equate these two. So,
work done by the system will be integral of minus k by x dx.
f dx, yeah. The function, it's a non-uniform force. So this work done by the thing, by this will be integral f, which is, I can fix the sign by physically. So I can leave the sign here.
Okay.
So x will be from 0.1 to 2.01.
2.7.
So this is a trivial integration. So x raised to the power -1. No, it will be log x, no?
Log x.
0.1 to 2.01. This is on 20.1. Log a minus log b is log a by b. Okay, so this is log 2.01 minus log 0.1, that is 2.01 with 0.1, that's 20.1. Okay, k value is given. So initial energy is half m 2 square, that is half m is 1. So half 2 square